All right, good afternoon. This is the physics seminar sponsored by the Eddie and April Lucas donation, which allowed us to bring in Austin Nelson today, one of our own students who did his bachelor's here and got that in 2019. Grew up in Kansas, stayed in Kansas for his undergraduate. Then he did PhD work at Oak Ridge National Lab and is now a postdoctoral researcher at UVA doing research at Jefferson Lab in Virginia. So please help me welcome Austin, who will tell us about the Neutron laboratory.
Thank you. Yeah, so thank you for that introduction. It's really nice to be back here in Wichita again. Right, I'll let him start sharing that. Yeah, so today I'm going to be telling you a bit about neutrons, more specifically avenues for testing the standard model using neutrons. Now, a lot of this is going to parallel along with what was relevant for my PhD work. Started that. Well, I mean, Olga already gave a very nice introduction, but yeah, from Kansas, came here as an undergrad. I recognize some of these people from an SPS outreach event. I went to the University of Kentucky for grad school. Started the pandemic there. And then I went down to Oak Ridge National Lab, where I helped to commission one of the two experiments I will showcase a little bit today. And then, of course, now I'm working on something completely different, more applied, spin polarized fusion. And I'm working at Jefferson Lab as a postdoc for UVA. We can certainly talk about that afterwards if you want, but we're just going to focus on the grad school stuff today. So I wanted to try to keep this approachable for a wide variety of people. I wasn't sure exactly who all was going to be here. So I try to keep this open and approachable to students, or really anybody who is not totally familiar with beyond the standard model physics research, especially in the low energy regime. But to that end, I will talk at some length about the context of all of this, that is, the standard model is, why we're actually studying it. And I will showcase a couple of experiments that are two different but parallel efforts that are going into this beyond the standard model physics look via neutrons. And of course, this would not be a talk about nuclear physics if we didn't first talk about the standard model. So that's where we're going to begin, introducing what our standard model in a nutshell is for the weak interaction. So really, the standard model is just a collection of our best models, our best ideas and theories about describing how matter interacts with each other. And that culminated in the collection of these fundamental constituents of matter, as well as fundamental forces that they interact with, as well as these bosons, which are the means by which those forces interact. And of course, that describes very generally a variety of phenomena, including things we observe, like protons and neutrons. But I want to focus a little more on one of those fundamental forces, the weak nuclear force. This is largely what governs nuclear decays. And one way I like to think about it is it's a sort of transmutation between quarks and leptons. And it's mediated by these two very massive bosons. A common example of that is neutron beta decay, by which one of the down quarks in a neutron exchanges a W- boson with an up quark, and that very, very rapidly decays into an electron and an anti-electron neutrino, giving us our final decay products. Now that's well and great, but if we actually want to do physics, we need to have some rigorous model for quantifying these types of interactions. And whatever we come up with needs to take into account the phenomenology that we have observed. One of the biggest ones is this idea of parity violation, the idea that weak interactions in general don't obey parity. Much like how this car is not obeying parity when you put a mirror up to it. Now, this was a bit of a head scratcher for some time to figure out a robust way of describing weak interactions, but what they came up with was this mathematical structure for what we call currents. These currents are what we use in quantum field theory to describe these interactions of these fundamental constituents. And the structure of that is based up on a current that behaves like a vector. That is, it obeys a parity transformation. It picks up a minus sign, and an axial or pseudo vector that does not. Much like how momentum is a vector quantity. So this is colloquially referred to as the V minus A theory, and that is, in a nutshell, what our leading standard model prediction is for weak interactions. And that's the thing we're trying to poke at. But in order to poke at that, we also need to talk about some of the nuances that are introduced with that. The first of those being that those quarks are never alone. They have some contributions by virtue of the fact that they are bound. And normally, we take into account that type of structure using these things called form factors. But for our purposes today, the energy scales are low enough that we can essentially treat these form factors as constants. And each the vector and axial vector part get their own contribution there. And I will refer to those coupling constants quite often throughout this. Or more specifically, the ratio of the two, this lambda parameter, just the ratio of these form factors. And lambda is going to show up in a lot of our experimental talk as well. But the other interesting phenomena and an avenue for testing our standard model is the idea of quark mixing. Now, the up quark or the down quark can transition into another. In the case of beta decay, that's just one example of that transition. But in general, these quark state, if you will, can sort of rotate. Or you can describe it using some form of a rotation. And that is that matrix we use to describe that rotation is what we refer to as the CKM matrix. Now, anybody who is taking quantum mechanics can tell you that this expression here needs to be normalized. That is, the probability adds up to 1, is where we get this expression here. But this expression is also one of many you can make about this CKM matrix, and it's a consequence of the fact that a rotation matrix needs to be unitary. In other words, a strong assertion that needs to be true if our standard model is correct is that the CKM matrix needs to be unitary. And so this is just one statement of that happens to be very experimentally accessible. So that's convenient for our purposes. So that's the nutshell of what our current standard model prediction is. But what about the open-ended questions here? What are things that we can poke at to try to find flaws, for example? Well, we can try to look for types of weak interactions that maybe have a different mathematical structure to it, like scalar or tensor interactions. We call these exotic interactions, if you will. And furthermore, we can test this statement here, the CKM unitarity statement, and see if it actually holds up. So this plot I have here is showing you all these colored bands are different experimental endeavors to try to measure these decay elements, or these matrix elements. And the overall consensus about what the combined VUD and VUS terms are is represented by our yellow ellipse here. And quite notably, that doesn't quite overlap with our black line here, which is the prediction we would get from this statement here. Now note that I'm leaving out VUB here because it's rather small, doesn't really make much of a difference in this overall statement. So we're going to ignore that for now. So it's then very interesting that we don't have an exact agreement with CKM unitarity. And so in order to get a better idea of why that is, one way we can go is just try to make our experiments more and more precise. If we go to higher and higher precision, we can kind of narrow these bands down and get a little bit more refined of an idea of what it is we're actually trying to predict with more certainty. And one avenue for looking at this VUD element is using beta decay. In fact, this red and magenta square or rectangles here are those exact efforts from beta decay. So just to recap quick, I have introduced this idea of V minus A theory. That's our standard model for predicting the weak interaction. And then I introduced a couple of different avenues for where that may fail. For example, these exotic interactions or the CKM unitarity. Now I'd like to talk a little bit more specifically about beta decay and how that is used to access this VUD element. And that will lead nicely into getting even more specific and talking about how free neutrons are used to get VUD out. So beta decay is really what we call a semi-leptonic interaction, just has an electron as one of its products, a beta particle. Now, a common example of that is clear beta decay, like I talked about at the beginning. But that can come in a couple of different forms. We can have a nucleus that is unstable. In other words, you have your nucleons all bound together. But the physics there is a little different than if your neutron is all by its lonesome. And so in the former method, there are some nuclei that can decay very readily. And there you can isolate VUD by just measuring the contribution from this vector coupling constant. But on the other hand, though, you are ultimately going to be limited by your structure corrections. Because, well, if these nucleons are all bound together, you have to account for the fact that, again, there's more going on in the background. So to date, while this is a very precise way of getting VUD, it's ultimately bottlenecked by some of the nuclear structure corrections that also go into it. But while the free neutron is not does not worry about those structure corrections, it can access slightly different physics. In particular here, we now have our lambda term, not just GV. And we also have our neutron lifetime here that are going to go into how we extract VUD. So the experiments are done a bit differently, and we can look at slightly different physics. But ultimately, they are two ways of measuring what we suppose is the same quantity. And experimentally, the former is more precise. In fact, the PDG value for VUD is largely based off of these types of experiments. But as I had alluded to in my abstract, using free neutrons to extract this VUD term has improved in precision over time. So now I want to dig in a little bit deeper into how we use those neutrons, specifically kind of set up a little bit of the context for doing specific experiments that extract VUD, or pieces of it, rather. So this long equation I put up here is the differential decay rate for neutrons. And I put that up here because there's a lot of interesting things to unpack from it. For example, out front, we've got all of our stuff like the electron energy, our VUD, our lambda, all that's out front. But here in the brackets, we have a number of corrections that show up from there. They are put in there in general to help characterize and leave room for any of these possible dynamics might be involved. Like, for example, this directional asymmetry. If there's a asymmetric distribution of what the angle is between the electron and neutrino, that would be picked up by this little a term here. Meanwhile, the possibility of exotic interactions contributing to this decay rate are encapsulated by this little b term, what we call the fierce interference term. And then over here, all these bigger letters that couple to our neutron spin are going to describe other avenues of things like other symmetry violations like parity or time reversal. Now, it's a very general equation, but it sets up possible avenues for trying to characterize things like parity violation in weak interactions or possible time reversal asymmetries. But if we go a step further and actually were to integrate all this, a lot of that would kind of get smushed into some constant, but we would get a prediction for what our neutron lifetime should be. Or if we flip that around, because the neutron lifetime is something we can actually measure, well, then that's how we get to our VUD expression here. But the main takeaway there is if we want to access VUD measurements from free neutrons, we need to measure a couple of different things. We need to look at some of these asymmetries here in order to get this lambda parameter, those vector and axial vector couplings. And we need to do other parallel experiments that aim to measure the neutron lifetime. So to dig even further down the rabbit hole here, we need to extract lambda from experiments. And in order to do that, our experiment that we set up needs to isolate one of these asymmetries or these possible symmetry violations. So if you had a parity violation experiment, you can isolate this big A or big B, and you can get lambda that way. Or you can instead study the phase space of neutron beta decay and try to pick up on any asymmetries that might exist there. Well, that's another way to extract lambda. Furthermore, if you wanted to look directly at possible exotic interactions, if your experiment is tuned to isolating or measuring this fierce interference term, well, then since the standard model predicts that to be 0, if your experiment finds that it's not 0, then that's potentially a very big deal for the standard model. So how about the neutron lifetime then? If we wanted to extract lambda, we do these asymmetry experiments. But if we want to extract the lifetime, I think that's, to me at least, a little more intuitive. And we have a couple of ways of doing that. One, I see Reed nodding because he knows exactly what I'm talking about. On one hand, we have a method of counting up how many neutrons you have left after you've stuffed some of them into a jar, basically. You put some neutrons in, you leave it sit for different periods of time, you measure how many are left, you get a decay curve out of that. You can measure your lifetime that way. However, do note that whenever you're doing this, your lifetime you're extracting is actually that of your trap. So if you have any leaks in your bottle, for example, that's going to make your lifetime look lower than it actually is. But on the other hand, if you count up the decay products, so your protons or electrons, in what I like to call appearance experiments, that is prone to different systematics. So for example, if you're not counting your protons as well as you think you are, then your lifetime is bound to go up. Or if the neutron is decaying into something else you didn't know before, well, then you would also see a systematic shift upwards. So yet again, two different ways of, or multiple options for measuring what's essentially the same thing. And from a scientific perspective, it would be very interesting to compare how those stack up to one another. And that brings us now to the current experimental landscape for these types of neutron beta decay studies. Over here on the left, I've got our value of VUD, and on the x-axis, we've got our value of that lambda parameter. So this big red band here is representing the value of lambda as is seen from most of these parity violation experiments, this big A term. Whereas if you get lambda from little a, you have this gold band here. Quite notably, they don't exactly match up. It's not a very stark difference, but it is still enough that you might be motivated to measure those again with slightly different attention paid to your systematic uncertainties. But the perhaps more exciting comparison is between those two different methods of measuring the neutron lifetime. There is, or at least was, I'll get into that in a moment, a whopping 4 sigma discrepancy between these two different methods, which is definitely not ignorable. And this ongoing neutron lifetime problem has spurred up a lot of different discussions. Everything from the more mundane, well, somebody's just missing or not taking into account something, all the way to people going as far as just putting forth the idea of new physics being involved. You know, maybe some of those decay modes that we didn't know about are there. But this is an active area of research, even since I graduated just less than a year ago. There have actually been some very interesting updates. The most notable one is just last Christmas, the JPark collaboration is a group in Japan that is doing a type of appearance experiment, but instead of measuring the protons, they're actually measuring the electrons in a time projection chamber. Now, initially, they had a very large error bar on their first pass measurement several years ago, but this one was refined, and it actually agrees with disappearance experiments. In other words, it kind of disagrees with all the other types of experiments that are looking at decay products. To me, that's pretty telling of what the underlying problem is, but you know, this result is still under peer review. But the other one, too, that I feel is worth mentioning is there was a very compelling idea of a possible excited state of the neutron that rapidly decays after the neutron has been born, if you will. And that could be used as a possible explanation for this discrepancy here. So again, these are pretty fresh results, all things considered, and I'm not going to necessarily be talking any more about them. I mean, we can certainly discuss it, but instead, I'm going to be focusing a little more on some of the other ongoing efforts. Right, so in case you don't like plots, I put a table up here instead with a variety of different collaborations and what value they're trying to measure, and then their more recent measurement result. Quite noticeably at the bottom, we have the 2 experiments I'm going to be showcasing to you today, which are the NAB and BL3 experiments, which are going to measure that lambda and fierce interference term, as well as the neutron lifetime, respectively. So just to recap our context here, I've introduced this idea of a V minus A theory, which is what we refer to as our standard model prediction for weak interaction. And in order to scrutinize that, we can look at things like non-vector or axial vector couplings. Or we can evaluate this lambda term and use that in conjunction with the neutron lifetime to pick out things like VUD. And that goes into our statement of CKM unitarity, another one of the standard model predictions. And one important way of isolating this VUD is from free neutron beta decay. So let's actually get into talking about some of the experiments here. Now, a little bit of a disclaimer, just in the interest of time, though I think I'm doing okay. I'm going to provide you with a little bit of a broader overview of these experiments, what it is they're trying to measure, how they're trying to measure it, and then an overview of some of the subsystems that are involved with that. I'd be more than happy to talk a little bit more about them afterwards if you have any questions. I'm not an expert on all areas of it, but there are pieces of each of these experiments that were very, very relevant to my dissertation, so I will do my best there. But we're going to start by talking about the NAB experiment. This is the experiment down at Oak Ridge National Lab that I worked on for a few years up until I graduated. This is a nice overview shot of the Spallation neutron source, which is a facility within Oak Ridge National Lab down in East Tennessee. You can see the Cumberlands in the background there. But over here we have our instrument hull where the neutron, or the proton beam is sent into a liquid mercury target, creates our neutrons via spallation, and it goes out in all directions down these different beam lines. And at the aptly named fundamental physics neutron beam line, we have the NAB spectrometer. So NAB has the express goal of measuring this asymmetry term, little a, to a relative precision 0.1%. To date, that would be one of, or the most precise evaluation of that term. But NAB also has the goal of isolating this fierce interference term to a precision on the order of 10 to the minus 3. So again, I'd like to talk more about how it is we plan to isolate those and the instrument we actually use to do that, and then briefly go through all of the major subsystems involved with that. So if we have a beam of neutrons that is unpolarized, then a good chunk of that really long equation I had up earlier goes away, and we are left with a little a and a little b term that is going to factor into our decay rate. Now, ultimately, what this little a term is coupling to is going to be the cosine of that angle between the electron and neutrino. And so if we want to isolate this little a term, we need a way of picking out our spectrum of these different angles here. Now I'll leave it as an exercise with the reader to use conservation of energy and momentum to find what the neutrino momentum is in terms of the proton momentum, because as I'm sure a lot of you are acutely aware, measuring neutrinos directly is not trivial. But if you were to do so, you could write down a phase space of available proton momenta and electron energies. You get what inside we refer to as the teardrop plot. And it's essentially a contour plot for this cosine theta. And we note that the height of this teardrop plot, this contour plot, is going to depend on your decay rate. If you pick out this, if you measure this entire phase space here, and you notice if there is an asymmetry present, then you're going to find a slope on your height of this plot, if you will. And so really the name of the game here is just after you get your spectrum, going through each of your electron energies and measuring the slope of that trapezium, if you will. And we do so because, well, that slope is directly proportional and dependent on A. Now, if instead you were to stop measuring your proton momentum and essentially integrate over proton momentum, you would get your entire electron energy spectrum. Looks something more like this plot here on the bottom. Now, little b is going to factor into that as well. It might shift it around, kind of smear it a little bit. And so what we intend to do there is take very robust theoretical models and simulations, essentially, and model or simulate this electron spectrum for a wide variety of different little b's. And the gist of the idea is that by comparing that to the electron energy spectrum that we measure, we can at least kind of get an idea of where little b might be at then. But from the experimental side of things, we can't really directly get the proton momentum out either. When protons are created in beta decay, they have an energy less than a keV at most. And that makes it very difficult, if not impossible, to detect. And so we actually have to accelerate those protons. But once you've accelerated it, well, now there goes your momentum. So instead, if we have some knowledge about where that decay happened and where our detector is, we can measure the time of flight and infer what the proton momentum was from that. But if we're going to do that very precisely and have a very good mapping between the time of flight and the proton momentum, we need to have a very good idea about what that path length that it took was. And, well, that's going to actually depend on a lot of different things. For starters, we don't know exactly where it started. And furthermore, all of any magnetic field impurities or anything like that, it's going to affect the total effective length that it has to travel. So all of these things are going to have to be taken into consideration when actually performing this experiment. Because if we don't have a very good mapping of that, then that's going to ultimately smear the edge of our spectrum there and limit how precisely we can actually get little a out. So if we want to do this precisely, we have to be very careful about taking into account a lot of these different details. Now, this is the apparatus that is going to make that happen, the NAB spectrometer. The journey begins with neutrons entering into our decay volume. Some of those will decay, and the decay protons are going to be directed upwards, and that's where they drift through what we call our time of flight region. And at the very end, they are accelerated to 30 keV, so they can punch through the dead layer of our detector. So we can actually pick them up that way. But that also means that our detector needs to be held at a very high potential of 30 kilovolts, which also means that everything connected to it needs to be held at a potential of 30 kilovolts. But the electrons that are produced in beta decay can be picked up on either detector, and at least relative to the protons, they pretty much show up almost instantly, as far as we're concerned. And we use the conjunction of what we predict to be an electron hit, like, hey, it had this energy, it happened in this region, followed by, hey, we saw something roughly 60 microseconds later that looks like it might have been a proton. Okay, well, let's just call that a coincidence event. We pick out beta decay events that way. Yeah, so as I mentioned, we have a high voltage cage on the top, which allows us to actually have all of our instruments in there, including things like our data acquisition system, held to that really, really high voltage. So our subsystems are up to a pretty tall task here. Again, if we want to leave room for doing systematic studies, then our subsystems are going to need to, okay, sorry. So anyways, the subsystems I would like to talk more about are the detector and electronics, our data acquisition system, the magnetometry effort, it's the effort to understand magnetic field, and then also our polarimetry. That is the thing that I've been leaving out, that initial assumption that our polarization has to be 0. Starting with the detectors here, NAB makes use of a couple of large area, very highly pixelated silicon detectors. Again, top one's held at 30 kilovolts, and those have the job of measuring the electron energy as well as that proton time of flight. But one thing we'll also have to do in the end is do a very, very thorough energy calibration just to make sure that we are very precisely reconstructing what the electron energies were. And this is the detector mount that goes with it, along with all of the shaping electronics that are responsible for taking that initial response from the detector and shaping it into something that is able to be digitized. Just to reconnect this back to some work I did on my thesis, though, I actually built a cooling system for electronics and then used that to perform a systematic study, at least to see to first order if there was any correlation between the signal we get out and what the temperature of our amplifiers were. Turns out really not much, but that was just one thing I did. Okay, next one is our data acquisition system. This one has a very special challenge for NAB, since each of these pixels on here essentially represents its own detector. And so we need 127 channels on both detectors, so upper and lower. And moreover, it needs to do more than just pick out what the energy was, where it happened, and when it happened. Because we want to do a lot of systematic studies on this, see how, say, for example, the timing response changes under certain conditions, then we want to save a lot of the raw trace readout, the raw signal that comes out of our detectors, which is very challenging from a data collection standpoint as well. You run out of space to store things very quickly that way. But moreover, these two chassis need to have a very stable and well-known offset between one another, right? Like one of the key things we need to know from this is the timing between our events here. And in the initial uncertainty budget for the experiment, it was determined that in order to keep the uncertainty down less than 3⁻⁻⁴, then we need to understand the jitter between this offset between these two chassis to within 300 picoseconds. Which it's one thing to synchronize all of these cards in one chassis. It's a whole nother thing to very stably synchronize these chassis that are 8 meters apart. So this is the instrument, the chassis that houses all of those ADC cards. We have fiber optic communication with them. It's how we actually communicate with it while it's under high voltage. We have 16 of these modules in each of our chassis, which each have 8 ADC plus FPGA channels. And they also have a what we call a ring buffer, which is essentially a memory buffer that stores the last microsecond, I think, or millisecond of raw trace readout on that channel, which is quite a bit considering it is taking 14-bit samples of what's coming out of that detector 250 million times per second. So it adds up very quickly, and there's a lot to chew through. But on each of our chassis, we also have a timing module, which is partly responsible for this custom synchronization routine we use to make sure that offset is very stable. Now, if we want to get more into details, or if you want to know more details about the hardware performance side of that, I would point you towards our published paper, which has most of those details in there. That was spearheaded by a good friend and colleague of mine. But if you want more of a software overview on that, I actually talked about how the data acquisition software works at some length in my thesis. But what I wanted to show here, at least, is just an example of some of those raw trace responses for some beta decay candidates. For example, a proton, which has a very low signal-to-noise ratio, which has some interesting and challenging systematic implications there. Then on the bottom, we have a much more clear response from an electron. And I'm also showing this plot here, which is was part of a study that was done by a postdoc to characterize the stability of that phase offset between our two chassis. And essentially, they had run the synchronization routine and initialized and reinitialized the software many, many times over, and were measuring what that offset was between the two of them. And so if you do that a bunch of times and get a width of your distribution here, that will tell you something about what that stability is. And it was determined to actually be way below our 300 picosecond mark, which is great. So the next one is magnetometry. That is the effort to implement and understand the magnetic fields that go into the spectrometer. So there's actually a few different magnetic fields that are relevant here. Of course, we have the large time of flight region, which is really just a long uniform magnetic field that's really responsible for essentially straightening out the trajectory of our protons. Makes it more predictable to get an estimate of that effective path length. But just above the decay volume, we have a magnetic filter, which is sort of a selector. It only selects a small range of outgoing proton trajectories. Anything beyond that would either take too long to actually get there or not get there at all. So we have a kinematic selector, if you will. But then down below, we have a completely different field setup that is meant to completely reject any protons that are going downwards. But the big one here is really understanding what's going on up here. If we want to know that time of flight, or sorry, that path length, so we can properly map time of flight to proton momentum, then we need to make sure that we know very well what that magnetic field looks like. And so there was an effort, before I even got there, to measure the magnetic field throughout the spectrometer and compare that to the prediction, and well, it turned out to be pretty good. But I think a lot of these systematic studies, since they were done a while ago, are up to probably being done again, just to make sure things haven't changed over time. The last one I want to introduce is the polarimetry effort. Again, one of the biggest assumptions here is that our neutron beam doesn't have any polarization. If it did, then, well, some of these terms out here are going to start leaking into our measurement. That's a systematic uncertainty. In particular, it was determined that in order to reduce the bias that would be introduced by having a non-zero polarization, to keep that less than 10 to the minus 4, then the net polarization needs to be less than 2 times 10 to the minus 5. And a team from UT, I think just last year or so, had finalized a determination of what that neutron polarization is coming in, and that was determined to be about an order of magnitude too large. which is then where the other half of the polarimetry effort comes in, and that is a way of reducing that. And that is done using this very creatively named device called a spin flipper. The idea here is that you take, you put it in your beamline, and your pulses of neutrons are going to pass through there, and half of them are going to have their spins flipped. And this is done by using this principle called adiabatic fast passage. Best way I have to describe that, it's essentially NMR in a box. It performs NMR on these neutrons as they pass through, and will flip half of them, with the idea being that over a long period of time, after you've averaged over a bunch of things, your net polarization will be reduced. So, like I said, one of the big things I did at grad school was to help put this experiment together, to do our proof of concept, if you will. That's commissioning. So a couple of summers ago, we took roughly 100 hours of neutron beta decay data, and we also spent some time putting radioactive sources into the spectrometer in order to do some rudimentary electron or energy calibrations. And all of that, well, we learned quite a bit. This is our time of flight spectrum of our protons. They came in actually quite a bit lower energy than we expected. You know, normally you'd expect them to come in at 30 keV minus some, but they actually came in a lot lower than that. So there's one thing that we need to work on. But nonetheless, all of this neutron beta decay data was put together into what, to our knowledge, is the first full reconstruction of the neutron beta decay phase space, our reconstructed teardrop plot, if you will. But since, again, this is commissioning, it is not the ideal setup. We haven't done a lot of the systematic uncertainties that or analyses that are needed to get a precision measurement out of it. So we have not released any measurement of little a just yet. But instead, we took a lot of, well, we had a lot of learning that, or we learned quite a bit from doing this commissioning run. And the time afterwards was spent addressing these different pitfalls and shortcomings. But if you do want to know more about how that commissioning went, or particularly on the analysis side of things and some other commentary, another colleague of mine, Frank, has put together our commissioning paper, which is currently under peer review. I think Reed knows Frank, actually, so he's another IU grad student. But yeah, there's a lot more details in there about the conditions of commissioning, and as well as some of the implications from that. But believe it or not, NAB continued after I left. And one of the big things was that campaign to fix and address a lot of those shortcomings that were observed before. Like, for example, the fact that our proton energy spectrum was way lower than we thought. Well, it turns out that we had unintentionally introduced a contamination dead layer on our detectors. Oops. So we have to figure out how to avoid that next time. And there was also a very extensive campaign to rework the detector electronics that I talked about before. More specifically, just how they're specifically laid out and designed. There was a lot of noise, let's put it that way. But the goal now, to my knowledge, is to take the existing data from this past summer and essentially stack that up against another experiment that is measuring little a, this aspect experiment. And then, of course, now is the time then to actually start digging into some more of these systematic uncertainties, these different things that are going to, that could limit the precision of our final measurement. And then going into next year, the idea is to start taking a lot more data with the intention of using this to eventually get our little a measurement. So this is the NAB collaboration, a lot of the universities and institutions involved in that. Now with the like 10 minutes left that I have, I'd like to talk about the other experiment. It's a neutron lifetime experiment called BL3. Now this is an overview of the NIST campus up in Gaithersburg, Maryland, where BL3 is going to be housed. Don't ask me where the instrument hall is. I've actually never visited this place before, but nevertheless, that's where it's going to be. Now, BL3 has the express intent of measuring the neutron lifetime to less than 0.3 seconds. As far as appearance experiments go, that is an incredibly precise measurement, much more so than what's been done up to date. So much like I did with NAB, I'd like to take some time to introduce what this beam method is that's actually underlying the experiment, and the idea that we need to focus on two different measurements and really understanding those very well, and then close out with some more of the outlook. So in order to get your neutron lifetime from this experiment, you start with your proton count rate. You have some detector that is measuring your protons that have come out from some decay volume. Now that's going to depend on your neutron lifetime as well as the number of neutrons you started with. Well, you don't really know a priori how many you started with, and to actually measure that directly is a bit convoluted, especially because it depends on information about the beam itself, like what the velocity spectrum looks like. Fortunately, you can also get this information if you, instead of measuring absolutely how many neutrons you have, just counting how often they're going through a different detector. You get your neutron count rate out of there. And doing a little algebra, we get our proton count rate in terms of our neutron count rate, as well as the efficiencies associated with that. Or rearranging that, we get our output for the neutron lifetime, which again involves two primary measurements, the proton count rate and the neutron count rate, as well as really well understanding how well we're actually doing that. But in the experiment itself, we also exploit this trap length here to probe any possible nonlinear effects that might be introduced there. So the actual decay volume here, the electromagnetic trap, is made up of a series of electrodes. Now, each end of that is held at some high potential, which is trapping any protons that are produced in there. Now, periodically, one of those is sent to ground, and a magnetic field directs those protons out to a detector. You can vary the length of this trap by just tacking on more electrodes, and you can take this proton and neutron count rate for each of those different runs, and you get a series of measurements that forms a line with your slope, depending upon your neutron lifetime, as well as all those efficiencies that you have measured at some other time. So from that line, from all your measurements, that's essentially how you would get your neutron lifetime out. Now, the name of the game with BL3 is to really dig in deep to all these different facets of this type of measurement. The original measurements were great. They highlighted a lot of things, but now we want to reapproach this method from a bit of a fresh start. Redesign, redevelop some of these subsystems with a lot more attention to the details this time. Now, this is the proposed layout for the BL3 experiment. Over here, we have our magnet and proton detector. So in here, you can see our electromagnetic trap, which has those series of electrodes, as well as our proton detector over here. But much like before, that also needs to be held at high voltage. In fact, there's a remarkable semblance between the proton detection scheme here and in NAB. The pixelation is, of course, different. It's more conducive to the goals of BL3. But the company that actually created this detector is actually the same one that created the one for NAB. So if it works, it works. Now then, the other facet of this experiment is measuring the neutron count rate. That is made up of a series of targets, and those targets usually have some kind of lithium-6 compound in them. The idea being that some of those neutrons can be captured by the lithium-6 and emit an alpha and a gamma in coincidence. So you can monitor those count rates to better understand or to gain knowledge of what your neutron count rates are. And for reasons I will touch on in a moment, these alpha and gamma monitors are actually very particularly placed in your neutron monitor. Now then, I'd like to focus a little more on the effort to understand the neutron counter efficiency, mostly because that's what's actually relevant in my thesis. I had a whole chapter dedicated to part of that. But historically, if you wanted to understand what this neutron counter efficiency is, you actually had to go to some other experiment and use their value for the cross-section of that neutron capture, which can be a bit cumbersome, and it also doesn't really address some of the other systematic uncertainties in there. And so in future iterations of the experiment, including BL3, we have made use or making use of this alpha gamma device, which is essentially a way of circumventing that and just determining what your neutron monitor efficiency is just right there in more controlled conditions. But one thing I did in my thesis, though, was I went back to that historic method and noted that there's a pretty large dependence on where the neutron beam is going through this monitor. And so that could be a systematic uncertainty there. You can't exactly guarantee that the neutron beam is going to be in exactly the same place when you monitored your efficiency and when you're actually doing data runs. So one way of getting around that is, well, using a very particular configuration and tilts of your detectors there. Because what that's doing is essentially adjusting the solid angle. And if you put it in just right, your solid angle can actually be relatively insensitive then to where your neutron beam is going through. So again, more details on that in my thesis. So, like I said before, BL3 is paying attention to more of these details here. BL1 had their initial result in 2005, but as you can see from this table here, they were pretty limited by a number of things, such as how well we understood, the absorption of those neutrons, and our statistics as well, and how well we understood the efficiencies. But nevertheless, they came up with a result with about 3 seconds uncertainty. So that tells you about where BL3 wants to be at. It's an order of magnitude lower. And in 2013, they implemented that alpha gamma device, and they actually used that same neutron monitor, several years later, measured its efficiency, and it at least made some correction to that and reduced the systematic uncertainty down further. Now, I won't say much about BL2, other than it is ongoing, and it's essentially a way of trying to bridge that awkward gap that BL1 kind of left there. But more to come from that soon, hopefully. But BL3 is different in the sense that, again, it's starting fresh. We're looking at these things from a fresh perspective. We have larger spectrometers so we can better understand our efficiency, longer trap, more uniform field, and a larger area detector. And to help with our statistics, we also have a bigger beam. So this is the BL3 collaboration. Certainly some overlap between this and NAB. But just to wrap this up pretty quickly here, at the beginning, I hope I succeeded in introducing this idea of beyond the standard model physics searches. That being searches and probes into this V minus A theory. In particular, looking at this VUD, ZKM matrix parameter. And then I introduced to you a couple of examples of two neutron physics experiments, which, while they're measuring two completely different things, they both go directly into this same idea. Now, again, these are up and coming experiments, so they haven't come out with the results just yet. But the hope here is that NAB is going to be coming out with their little a determination within the next couple of years. And then BL3 is set to start commissioning fairly soon as well. So with that, I would like to thank you again and open up the floor for any questions.
Yeah, any questions? Sean?
I had one about, just right near the end of your second section
Mhm.
about the first experiment, the count rate simulation and actual plot.
Yeah, it might be easier just to, oh, sorry.
In the count rate, I noticed, yeah, you have negative counts per second. How do you have negative counts per second?
I think that is an artifact of the background subtraction routine. I believe. I was not the one who did this analysis, but my best understanding is that after you try to take into account some of the backgrounds, some of those low populated bins could be sent below zero.
All right. Nick?
So back on slide 14.
Okay, I'm just going to do this. Yes.
Yeah, that term there, mass of the electron over the energy of the electron. I guess that really is mass of the electron plus the mass of the neutrino.
Yes.
But of course, that's 600 different, unless it's what's being found that the electron neutrino might be mixed together.
Yeah. Yeah, and I presume the tau neutrino component would probably be this. Maybe. That's an interesting point, though. I mean, it's a pretty advanced problem to derive this whole equation for yourself. So, yeah.
BF is non-zero anyway.
Yeah, exactly. That's exactly. Which, it's interesting, though, because
Valves were also found.
yeah.
I always worry about that because I had a similar concern when I worked at PU.
Interesting.
Matt?
Okay.
Notice slide 82. Yeah, so this one. So I was curious what happened in 2005 with disappearance measurements, because it looked like they changed from being integrated. Is there a change in the count? Do you know the history of N?
Not the extensive one, but I know, for example, like this data point and this data point is BL1 and the correction that came from that.
Yeah, the black. What is that?
Oh, yeah.
What happened? The measurement, that one, yeah.
So I'm actually not sure what this measurement is. There's certainly been a lot more variety of disappearance experiments that went on with different types of traps. I don't exactly know why all of a sudden the precision went way down. I would presume there was some technological advancement, though, that.
I heard in 2000 about the same.
Yeah.
Just curious.
I don't know the history of that one specifically, no. All I know is that, well, at the very least, this is UCN Tau, which is the most recent one that came out a few years ago.
Presumably, they still all employed blind analyses, right? But yeah, still looks suspicious. Yeah.
Yeah.
Go ahead.
I just wanted to ask on this plot, you said that the appearance measurements in 2020 and 2024 were the same experiment, just like they're crazy different. But what happened there?
I remember reading through the paper from 2020. I don't remember exactly what the reason was why they had to say, okay, well, our uncertainty is large for the time being. Yeah, so I haven't memorized all the details on that, but yeah, though I will say, just to get into some of the methods here, when I was computing the average here, I did weight it by the inverse of the uncertainty, so I don't think it would pull it too much upwards, but I mean, you are right, though, it would sway it a little bit.
Talking about the way that you struck a beta decay, about how you detect the electron first, and then you wait 20 microseconds, you detect the proton in the upper vector, right? How do you know that they came from the same beta decay? Electrons.
Right. So this is actually where the virtue of having a lot of pixels is at. You can get a lot of spatial resolution there. So the idea is, yes, we have a lot of electrons that come in, but we actually don't start flagging a potential beta decay event until we see a proton candidate first, which is, to get into more of the algorithm here, if an event happens within, say, not on the edge, for example, of the upper detector, and it has a certain energy that corresponds to roughly 20 keV or so or lower, then we say, okay, well, this is potentially a proton. And that's when we start sifting through all the other backlog of triggers, and we say, okay, well, these ones had an energy that is reasonable for an electron. They also happen in a time window, consistent with what we expect for beta decay. And they also happened within a region around that initial point, that proton point, on either upper or lower. So we perform cuts in real time, basically, just to position, energy, and timing cuts on it, just to narrow it down that way.
So detecting the protons kind of rarer than the electron, or with the proton.
Yeah, the proton count rate is a lot lower than the electron count rate, especially because there's a lot more things that might look like electrons than protons.
Well, all right, we are over time, but it's always nice when there's lots of questions. So thanks, Austin, for giving a very nice question.
Thank you all for having me, and thanks for listening.
Yeah.